Howdy, everybody. Hope you're having an amazing day, evening, night. I don't know why I keep saying that. I hope you're having a good time, whatever time it is, wherever you're at. I'll have to find a more generic way to say that. But I truly do hope everything's going well with you and things are going great. And I just, again, want to keep saying thank you for your comments and the solutions you provided. I tried to go comment on everything. I promise I'm looking at code and looking at things like that. I find it very interesting. And I changed some things up today. And even hopefully I don't spend too long talking about the first part. And if we do, we'll get to some of the work that you guys had done, or you all have done, have made me think about making a little visualizer for it. So we'll look at that as we have time in the video. But again, just thank you very much. So really appreciate it. We're continuing to work on this intcode computer. I think it's a lot of fun. It's a great way to try things out and to learn new things. Even if you're learning a new language, besides just the fact that I think it's a good refresher of how a computer works, it's kind of a cool way to learn the intricacies of a language that you're working on and focusing on, right? So this one in particular is pretty cool because now we're talking about how can we get these different computers that we built or processes that we built to communicate with each other, and how do we do that? And so that's what we're going to talk about today. And with that, I mean, let's just get into it. So if my head's in a weird place, it's because you'll see a little bit later. But the idea is for day 7 is what we're talking about. Is they have these amplifiers that are connected in a series, and they even give you kind of a graph here. And basically you send an input to the first amplifier, it does some processing, sends it to the second, and it does some processing, and it outputs its results to the third, and so on and so forth, until you get to the end here where the output is sent to the thrusters. And that's the thing, right? So the idea here is you have your intcode computer, and you're going to do some processing on it. And last time, right, we created inputs and outputs, and I think I just used a list at the time. But now we're going to be chaining them together, right? So there needs to be some notion of, the output of A should go into B, and the output of B should go into C, and so on and so forth. And so, especially in part 2, I still think you could do it as a list and just kind of track it yourself and maybe be specific about it. Because even if part 2, if you trace the code and what it's doing, it's still very linear in series. Like A does its work, and then B does its work, C, D, E does it work, and then it wraps back around and continues. But I thought it would be good to kind of showcase the way channels work in Rust and the way threads work. And so that's what we'll be talking about today. At a higher level, though, I want you to think about what's happening here, right? Is we have some program running, we have program A running, and it's doing some processing, and it's spitting stuff out, and the results of what it spits out should go into this program B right here, right? For our intcode computers. I'm going to try and call them processes now, our intcode processes, because even though they are computers, we kind of treat them like a process, like we would in the computer world. So sorry if the terminologies get a little confusing. Anyway, if you have any ideas on how I could make it more clear, I'd be happy to do it. But the idea here is we're going to be chaining these things together. And this actually shouldn't feel foreign to you. If you think about taking a computer, having it do some work, and taking the results of that work and sending it somewhere else to do some work. That's not totally new, right? So, and that's really what it's asking you to do for this problem is, can you do some work with your intcode computer and send the output of that work to another computer and do that so on and so forth until you get to the final answer. And that's how you solve part 1. And like I said, it's not much different than what we've done in the past. Oh, I don't want to look at the code yet. I think I want to look here. Nope. Here. So if you've used a terminal before, you've probably done this type of work where you're like chaining outputs and sending them to other processes before, right? So here's a real simple example. Maybe I can just show it to you in my terminal. If I, do an ls, it's going to print this stuff, and I can do like a sort by size, and then that will give me the size, but maybe I want it in like largest to smallest, so I call reverse on it, right? If you think about what I'm doing here when I'm running these programs, I'm running three sort of distinct programs. I'm saying ls, which is, list the files in this directory. And then I want those listings to be sent to the data that comes out of that ls to be sent to this program called sort by, and I'm going to sort by the size. And so that's going to do the sort. And then I'm going to have the output of that go to this reverse program, which is going to reverse that sort, right? So these are called pipes in Unix, Linux terminology. They may be called that elsewhere. I'm just mostly familiar with Linux. And so, but the idea is what you're saying is, hey, the output of this should be piped to the input of this. And internally, you actually create a little pipe, is what it's called. And the idea is whatever's coming out of here is going to be forwarded to here. And then whatever comes out of here is going to be forwarded into here. And then this will be output to the terminal. So it literally looks like this, right? Is ls is going to produce some data. It's going to go into the sort by. It's going to do its work and produce some data and send it to the reverse, and it's going to do its work and send its output to the terminal, and eventually you get there to the end, right? This is all just an illustration to say, if you're not familiar with like this interprocess type style of communication, this piping and channels, or what they're also called in many languages, this is very common. You've probably already done it. You just maybe haven't realized that this is the name that it's used for. So the reason why I mentioned that is a lot of people, when they first start working on this stuff, get very confused. And there are some gotchas you have to be careful with. But that being said, the overall idea is not that difficult, right? Again, it's just, I'm going to have one program do something and produce some output, and I want some other program to read that input and do processing it on it and spit it out elsewhere. And you can chain this all over the place and do multiple commands, right? Like, I remember when I was first into Linux, I had several times where I was writing shell commands like this that were like, 10, 12, 15 things deep, where I'm piping things all over the place to sum up data and do things that you normally do in like maybe Excel or something like that, right? But I thought, nope, I can do it in the command line, and so I did it, right? So anyway, that's what we're trying to do here for this program. And the way that you would do, again, the way you do it on the command line is these are just programs, right? And you're saying, hey, run this program and spit it out and send it here, and then run this program and send it out, and or run this program and receive this stuff and then do your work and send it over to here, right? In Rust and other languages, the way you would normally kind of do that work is in threads. At least what I should say is what you traditionally do is if you have multiple things that are kind of doing their own work and maybe need to communicate with each other via channels or those pipes, is you'd use threads. A more modern approach, which I actually think I'll do a video on next time, will take the code that I'm doing now in threads and do it using asynchronous programming. So you can kind of get a comparison and contrast of how they work, and the pros and cons. But traditionally what you do is you'd create a thread, right? So old school, if you've done work in C or whatever, you create a thread, you call pthread create, and that starts a process. It starts like a new thread running in your program. It's something separate, doing its own work and doing its own processing, right? And that's kind of what we want to do here in Rust, right? You can think of each of these amplifiers, the work that we're going to be doing in each of these amplifiers, as kind of their own little thread, right? They're going to be a process. They're going to be doing their own thing and they're going to be doing their own processing. So we'll put them in a thread, and then we'll let them do that work, right? And so that's the first part of it, right? Is we want to have these threads that allow them to like do their own work and process with each other. And you can see the way that that works is we call this thread spawn here. And we just essentially allow them to all do their work. And eventually, once the work is done, we can join them together. This is just a simple way of saying wait for all of them to finish. And then once they're all finished, all the work will be done by the threads and we can be done. So the only thing we need to worry about then, besides the threads, is this part right here, right? Is how do we communicate with those threads, right? How do we do that? Excuse me, I got to grab my thing. If we have, amplifier A right here and amplifier B right here, how do we get them to talk to each other, right? And again, if you've ever done like Go, channels are the way to do this, right? And Go routines would be these processes. We're just gonna use threads, but we're gonna use channels in Rust, and these are akin to channels in Go, with some slight differences, but largely the same, right? The idea is when you create a channel, you have a sender that is used to send data on the channel, and then you have a receiver that is meant to pick up the data, right? So you kind of think about it as two ends of the pipe. So in this case, the sender would be right here, and the receiver would be right here, right? So this pipe that's being created, there's this end of it and there's this end of it, and you can think of the sender as this end and the receiver as this end. And so LS is going to put all of its stuff on there via the sender, and sort by is going to pick up all the results with its receiver, which is getting the data from right here, right? And so that's what these channels do. And they have some examples, right? You can think, and even here they're using a thread, right? Is the idea is you have some thread that's doing some work, and it's going to do, maybe it's an expensive computation, it's going to do its own work in its own thread. And then once it's done, it's going to send that result out here. And then this receiver is going to wait and listen for that result, right? And we want to do that exact same thing in our case, right? For these amplifiers, we want to say, hey, I want to do work here, and I want to send it to this amplifier, so it knows that, so it has the stuff that it needs to process, right? And it goes through and discusses how it wants you to do this. I won't go over to the problem itself. I kind of want to focus on the threads and the sending and receiving. But again, the idea is what they want you to do is set up these programs and then send different phase settings to them to figure out which one gives you the highest value, the best value. And so, we can just kind of do a bunch of permutations on all of the phase settings and to find the best one, and then do our work. But the core to it again is, can we set up these processes with threads, is at least what I'm doing today, and then can we use channels to have them communicate to each other? So given that, I think we should just kind of look at the code and get an idea of what it looks like so you can see how it works, right? So let's start with part one. So again, if you remember, we're going to want to set up all these amplifiers and hook them together, and then get them to kind of process one after the other, right? And like I said, we want to use channels to do this. So that's what that looks like, is right here, where we say, hey, create a channel and give me a sender and a receiver. I want to track the first one because we want to kick off the process. In the problem, it says, okay, so, you set up all these things, and the first thing you do is you send a 0 to the initial one, and then that will kind of start off the process. But the first thing you send to each of the amplifiers is the phase setting you want to test, right? So you can see I'm doing a for loop here over the permutations. This is a package I wrote a long time ago. So if you go look at it, it might be terrible code and I apologize. But basically it's a permutation generator. So if you say, hey, I want a new permutation on 5 items, it does work with, there's another struct called combinator, or I think is what it is, combination. And the idea is you can do combinations as well. In our case, we're just interested in permutations, right? So maybe I should show you the problem is they what they want you to do is they want you to try different phase settings. So there's the phase settings are 0 through 4, and they want you to like send those phase settings to each of the different 5 amplifiers, but they don't know which one is the best, and so they want you to like kind of iterate through all of 5 of them. So A will get a 0 one time, but maybe its best one is a 4. You just have to figure out which one is best, right? And for me, that was, that seems like a permutation, right? You've got 5 values, you just want to rearrange them. How do you want to rearrange them? Well, you had to test all of them, right? Because you want to find the best one. You could actually, to be honest, if you looked at the program, you could see there were operations that were doing just low value adds and then high value adds and then low value multiplies and high value multiplies. And so you could probably figure out where you wanted to do it just by doing that. But I just did it in a for loop with permutations, right? And so the idea here is I'm just going to go through all the different possible phase settings. And then for each of them, we're going to send that phase setting down the channel, and then we'll kick off the process. We went down a long path here, but the way we kick off the process is down here at the end is we send a 0 to the first amplifier, and then that will get things running, right? That amplifier 1 will do its work and send its results to amplifier 2, and so on and so forth till you get to the end. But let's go back to focusing on the channels, right? So the way that you work with a channel in Rust is you call this MPSC channel function. So MPSC, it stands for multi-producer single consumer. What that means is that's just a fancy way of saying you can have multiple things that are sending, but you can only have one thing that's receiving. So this receiver is kind of, you can't clone it or copy it. But the sender, you can clone as much as you want, and you can send as many things as you want down the pipe. You can only just have one thing reading from it. And that's good for us. That's all we're interested in, right? Is because there's kind of a one-to-one mapping, we don't have to worry about that. But we do want to track the first sender, because once we've created all the chains down here, we want to do that initial send to stick it off, right? But so how does the chaining look? It's actually not that hard, right? Is you can see like for each iteration for each value in the permutation, we're going to create a new amplifier right here. We're going to create a new amplifier, and we're just going to do we're going to send the phase setting we want to test, and then on the channel, and then we're going to create a new sender and receiver because we want to create the links. And this, it might look a little confusing at first, but if you think about it, our sender is going to be the previous sender, and our receiver is what we want in our current iteration, right in here. And then we're going to create a new sender and receiver, and we want to have the new sender, but the new receiver is going to be for the next one, if that makes sense, right? So if you think about while we're doing the creation in this like LS example, if we're like right here, we want this part of this pipe, right? And we want this part of this pipe right here, right? And so that's all I'm really doing. I'm just doing it in a for loop. But basically what I'm saying is, hey, I'm going to create in this iteration, I'm going to create this new channel right here, this one right here. And I'm interested in this thing, but I'm also interested in the previous channel's output right here, right? The receiver on this end, and I'm interested in the sender on this end. And so that's what I'm just doing in this code here is I keep this sender and receiver, and those are going to be like the current sender and receivers that I created at the end of it, right? You can see I do the update right here for the next amplifier. But in the between time, before I actually update those values, I want to create a new pair. And then for the new program I create, I want to set its receiver to the old receiver, but the sender is the new sender. And notice I do a clone here again, because the sender is clonable. We can clone this, right? This thing is going to take control of the receiver and nothing else can use that receiver, but this sender I can clone. And that's what allows me to call first here or do whatever, right? So that's what I'm doing in the code here. So you can see what's happening in part 1 is basically we need to do two things, right? We need to create this process, and then we need to create this channel and this channel. And it turns out for this process, what we're interested in is the receiver of this channel and the sender of this channel right here, right? So hopefully I explained that and it makes sense to you all what's going on. But once we have all our programs for part 1, we can just tell them all to run in order, one at a time. Process 1, finish it. Process 2, finish it. Process 3, finish it. And they're all outputting to each other, right? And so one's outputting to one, and those are all being stuck on kind of like a queue, the way to think about it. So when the one runs, it has all the stuff it needs. But basically, we just run them all through. And then when we're done, the final receiver should have the output, right? As you can think about, is our program is the terminal, our main code is the terminal, and so this output will have like the max value, or that permutations value. And so we just need to receive that and compare it to our current max list, and once we're done, that gives us the solution. But all this is to say, we haven't actually used threads yet. We'll use that in part 2. But again, all this is to say is you can kind of use these channels to communicate between these processes. Our actual code, though, if you look at the process, did not change much. And I broke this up into multiple files so you can see, but most of the code didn't change. Like, for example, if we go to the parameters, for example, you can see like the code is largely just the same. I added like some display values here for the terminal UI that we're going to look at in a second. But the same thing with the instruction. The instructions themselves didn't really change, right? We still have these like these type of instructions, and they look all the same. Again, I did add some code here. You'll see me using these in some other code where the UI is interested in things like, hey, how many parameters does this instruction have? And how many of them are positional, so I can see where they point to in memory. And then I do a display so you can kind of get an idea of, as opposed to it just being numbers, you can actually see what it's actually outputting in the UI. But that stuff doesn't really change that much. And if we actually go to I renamed it from a computer to a process, because now we're doing like multi-processing, I don't know, is the way to think about it. Maybe that's not a good answer in the end here, but you can see that like it's largely the same. You still have a bunch of instructions that you need to create, and you still have or that you need to figure out like what the next instruction is, and that really didn't change from last time. You still need to evaluate the instruction, right? So you need to say like, oh, okay, well, if it's an add, I need to do that add, right? None of that changed. The part that kind of did change is this part right here is where we do the receive, whereas before we were just pulling it off of a vecdeck, I think is right, is what we were doing last time. We now need to call these receive functions, right? And if we're outputting a value, we need to call send on that value. And that's the way these channels work, right? Is on the sender, you want to send values, so you call send. And on the receiver, you want to receive values, so you call receive. And the underlying implementation of the channel does the work for you, right? It will block when there's nothing there, and then when someone sends something, it will process it for you, and then you can do your work with it, right? Once that value is there available to you, right? So But I do want to just take a second to kind of talk about the power of these channels. When I first was learning programming, using like epoll or pthread create in C or whatever, those things are really powerful and they're really cool. But the majority of the time I was using them, there was no like communication necessary, right? Like think if you're writing like a very simple HTTP server, you can spawn a thread or a Go routine or whatever and just have it do its work, and it doesn't really need to communicate with anything else. The need to communicate with things or to like use these channels to communicate are very powerful. And in fact, Go says it really well. And I actually think maybe it's in the docs. It might be in here somewhere. Anyway, there's some cool things where they say like these channels are really powerful, and I truly believe that. Learning the channels from Go really helped a lot of me understand of like, hey, this is a great way to communicate between channels, is to send information between them, use these channels. And the nice thing about it is, what I should say is, it's abstracted for you, right? Is you don't have to worry about, do I have to wait? Do I have to poll? Do I have to do all these things, right? Like, how do I know when I'm done? That stuff is all kind of done for you over the hood, or under the hood, I should say. And so you don't have to worry about it. I should add too, if I'm not explaining this well, there are some really cool, I think I showed you the threads one, this Rust by example. I'll send you some links there that talk about threads and channels. They're a good way to learn about them. There's also the Rust book talks about these a little bit, I think. So I'll try and send you some links to read more about how they work. But again, if you're familiar, I think you'll, especially if you've come from somewhere like Go or whatever, and you've used channels before, they'll look a lot similar to that. Just maybe like there'll be some intricacies in the details. But using these senders and receivers, again, is very powerful. It allows you to like do processing and communicate when you need to communicate and wait when you need to wait and stuff like that. Obviously, async await is like the newfangled cool stuff, and we'll talk about that in the next video. I think I'll change all this stuff to using async await, but these are still really powerful tools. And even if you start using async await, you will still be using channel-like structures, right, to communicate between the services and processes, or I think they're called tasks. Anyway, so that's it. That's it for part one. Again, the code doesn't really change much. It's just the difference here is now instead of pulling from a list or a vecdeck or whatever I was using before, we want to call this receive or this send function to send and receive between the two things. And so you can see how simple it was. I guess is the point. That it's very powerful and simple. Is you just say, okay, instead of using a vecdeck, I'm now just going to have a sender and receiver. You can see here, in my process, I now have a sender and receiver as opposed to a vecdeck. And all I have to do then is just either receive or send when I'm getting output or input, right? Depending on what I'm getting, I just do the corresponding call on those things, and that's how it is. Or that's how simple it is, right? So, and we can see it running. I'll process it here, right? So you can see my solution. There you go. There's my answer to part one. Again, you're just running it through and doing your processing. So how does it change in part two, and why do we want to? So in part one, I didn't actually use threads, but in part two, you definitely do want to use threads, I think, especially if you're doing this async await. Again, I think I said this earlier, you technically don't need to, because when I was watching the code run, it always happened in like a very linear fashion. Like A would process, and then B, then C, then D, then E, and then it would go back and forth, right? And so there was always this point where one was waiting on the other, and you just kind of could go through that. So you technically don't need to, but I thought I'd showcase threads here. And why is it good? Because what they actually say is there's actually a feedback loop that they want you to install. So instead of E being like the end and being here, they want you to send the output of E into A and just keep doing it through the amplifiers until all of the programs halt, right? So the idea is you're going to kind of slide through these a whole bunch of times, and eventually they'll all stop, and the very last output of A, which would normally go into E, or the output of E, which would normally go into A, is the answer to your thing, right? So they show you here in the graph. And so why do you want to do this? I mean, technically you could do a for loop and a for loop, but using threads here is real nice because you can just say, hey, just run A, run B, run C, and so on and so forth in their own thread. So they're doing their own processing. And then you as A finishes, it can send outputs to B, or as A does its work, it can send its outputs to B, and B can then do that processing. And if at any point, for example, like C is waiting for something, it doesn't like stall or anything like that, right? B is in its own thread, so it can keep processing, and C can just wait until that thing is available to send that thing down the loop, right? And that's the power of threads and processes, right? Like if we go back to this right here, this sort by may have to wait until it's received all the input of ls before it can start sending stuff to reverse, right? Because like the very last value in ls may be like the first value that should be output to here, right? And that's okay though, right? If sort by is running in its own process, doing its own thing, and not interfering with ls or reverse, it can just sit there and wait until it gets input, right? And or did I say that wrong? I think it's the other way, right? Reverse can just sit here and wait while sort by is doing its work and ls is sending its stuff through, right? So you imagine ls is sending values here, sort by is holding off because it doesn't know when it's got the first value until it's received the last value, and reverse is just chilling, right? It's just doing its thing, waiting until it receives some data by sort by, right? That's the power of these threads, is they can all kind of do their own thing. They can all just kind of when they're waiting for input, they can wait for input, and they don't have to do anything special. You don't have to do anything special to manage, how do I know when what is running and where what is, right? So again, if we look at what we're doing here now, we're creating this weird feedback loop, right? So we want to be able to have what's going into E come back into A. And, so maybe A is waiting for E to do its processing. It has to kind of sit there and wait until E is able to spit that back out. But it can sit there and wait, and all these other things can do that processing, right? And there's no need for you to worry about it because you all have them in their own threads. So what does that look like for part 2? Well, the code actually doesn't change that much. All we do now is we just spawn them in their own threads, right? So we say, in fact, if you look at the code, it really doesn't look that much different. We're still creating a bunch of permutations. We're still iterating over the values in that permutation. We're still tracking the first, so we can kind of kick it off. I think we kick it off right here inside instead of outside at the end. But what do we need to do to hook up E to A? Well, that's just this line right here. Since we've tracked the first, we know that if we're on the last amplifier where I equals 4, instead of using a new one, we now want to use the first sender, right? So we want that, and so this is, you can think about it as this code as doing this part right here, right? It's going to, link E back up to A until the whole process completes. And so we have to do that. And then what do we do to create our thread? Well, we just call thread spawn, but the inside code here looks largely the same, right? We still create an amplifier and we tell the amplifier to run, but the kind of magic behind the scenes is we've spawned a thread and now it's doing its own work in its own, I mean, it's not a process, but its own thread. It's an OS thread. It's doing its own work, and the other threads can keep running, and your main thread, right, can do its own processing and running. And maybe that will help too if you're very new to threads and this isn't making much sense, is even your main process is a thread, right? And normally if you're waiting for input, you'd block, right? Well, you don't do that here because this is being put into its own thread doing its own thing, right? And that's it, right? So that's really all that changes here is we now call thread spawn. We do have to do some magic in Rust, not really magic, but some special stuff in Rust. Notice I'm calling move here, and what this is saying in Rust is I want any values I use in this closure, I want to move into this closure. That is, they take ownership. So we use the move here. And what that means is for anything that we're using in there, we need to clone it so that this thread can use it, but also the other threads can use it as well, right? So that's what we do. We have this we create the amplifier and we run it, but we clone these values so they can be moved into this thread. And because we don't necessarily know when we're done, or how do I say this? When we're working on this, like the question is like, how do we know when the feedback loop ends? Well, it kind of tells you that the feedback loop ends when all the processes have halted. So like all the processes will finish, all the threads will finish, and that's when you know you're done. And so when thread A, when the amplifier A finishes, we just want to know what its last input was, and that's like the answer to the problem. So that's what this code is doing right here, is we say, hey, if we're amplifier A, I equals 0, then we should update our max value based on what its last input is, if that makes sense. One thing too is how do you know? So let's talk about this. Is how do we update our max values? Think about here in part 1, we just kind of ran all the computer, and once the computer was done, we did a final receive and then updated our max. Well, in part 2, we don't know when that's going to happen, right? It's going to loop around forever, and these are all running in their own threads. So we don't really know when we're going to get this thruster value. And the way I implemented it, maybe not you could probably use a mutex here, an arc and a mutex. But the way that I implemented it was I said, okay, I'm going to create another channel and have a max receive and a max send. And the idea is each of the threads will have that thing. And then I'll know if I'm the amplifier A, I can send to that max channel to that final input that I receive, and that will be the max for like this permutation. And then all I have to do is receive on all those channels till I'm done, which is what I'm doing right here. Is you call this max receive iter function, and what this does is it just calls receive recursively until all of the senders have closed. And this is actually a little bit of magic in Rust, whereas in like Go, for example, you have to be very explicit and say, oh, I'm going to close this channel. In Rust, that happens when the sender goes out of scope, right? So we create a sender for each of these threads, and the send only though goes out of scope once this thread itself finishes, right? So this block right here that I'm highlighting is when it actually goes out of scope. And so that's when the sender would close and say that I'm done, right? And so we've created one for each thread, even though it's only used in amplifier A, but they will take care of closing themselves. The gotcha that you have to think about though is we created a sender right here and we have to send that one. And so we do some magic here and we say, hey, drop this sender, so that when all of the senders have closed, this for loop will finish and this will give us our max value. So this is all just to say that we're using threads now, but we have to be more mindful of what we're doing in the threads, right? And that is to say, if we're expecting to get data from the threads, and we're going to loop over those things, we have to be aware of how many threads we're working with and when we're done, when all those threads are done, right? I think would be the way to think about it. Okay, so given that, sorry, I'm just looking at my notes here. There's a lot to talk about today. And if this is confusing and you are really interested in threads and I didn't explain it very well, I tried to like just do it with this problem, but I'm happy to talk about threads more. And maybe in the next video, I think I'm gonna convert this over to asynchronous programming, which is at a high level the same idea, that you can do multiple things and you don't have to worry about, those multiple things interact. You don't have to worry about those things doing their processing until they have to interact with each other. But maybe going into that will help explain it a little bit more as well. But again, I hope you get the idea of what are we doing here. We're just creating threads they're doing their own work, they're doing their own processing, but they do need to communicate occasionally with each other. And then at the end, they need to communicate to the main process is like, hey, I got some final value that's the output of my solution, of my permutation. And that's where we're using channels here to like act as like that mechanism for communication, right? And I will just say, here's part 2. It's done, right? I was able to solve it with part 2. But these, again, I think I've said this before, are super powerful. When you understand how channels work, and when we get into the async await, is Tokyo has several different types of channels that you can use, or channel-like structures that you can use, I guess I should say. Being able to use them correctly and knowing when to use them can greatly simplify your code and help you reason about your code easier. And that's, to me, what makes them powerful. When I say they're powerful, that's what I mean by them, is you can do really cool things with them, but you can do it very simply. It doesn't require a lot of effort on your part to do really cool things with them. So that's it. Again, just at a really high level, these ideas of channels is, hey, I want to send and receive data, and I want to process. I want to send and receive data between threads, is what I should say, or processes in our case, as the program is, and the ability to do that, saying, hey, I want to send some data on the channel, and hey, I want to receive some data through another thread, is very cool, and it simplified the solution to this program, right? Again, like I said, if you think about what the problem is asking you to do, there's not actually, the computer programs themselves didn't change, right? You're still just loading a program and processing it. It's just how do you hook them up to each other? And if you use something like threads, I think it can make that process really simple. Maybe it doesn't look simple. I don't know. It seems readable to me, but the idea that, oh, I can just create some channels and hook them up to each other, at least for me, really made a lot of sense, right? And simplified that process. Okay, one last thing I want to talk about. I know I've already gone 40 minutes or so, but I saw some code where you were doing, I think it was Gordon 508 again. I love seeing your work, but it looked like you were doing some debugging or wanted to like kind of see what it looked like and stuff like that. And I thought that was a cool idea. And so I went down the rabbit hole and probably took it too far. I don't know. I think it was fun. It was good to learn for me. And so that's why this is actually, usually I try and release these earlier, but I really went down the rabbit hole of, could you create a terminal user interface, a TUI is what they call it, to kind of visualize what these programs are doing. And so that's what I did here, is I have this run TUI function, which if you pass I'll show you how it looks. If you do this, if you do a cargo run and then you pass the -t, if you're not familiar, this -- says like all the rest of the parameters are for the program cargo, and not for like the build or the run that you're doing. So if I do this, it goes and it creates this intcode computer terminal user interface that you can look at, right? And it allows you to kind of step through it. So it's not very full featured. It's not, the best one out there. I'm sure some of you could do a much better job, but I wanted to learn how to use it. And I'm using Ratatui is what it's called. It's a cool little library. I think he's actually the person who's doing it is speaking at FOSDEM this coming week. So if you're interested in Ratatui or how this stuff works, I won't go into too many details. But the idea is you basically just say, if you've done web programming or whatever, you can think about, you kind of have these like, what do you call, what does he call them? Widgets. You have these like widgets that you put in there, right? Like in HTML, you're using divs and spans, and you modify those things, tables, those type of stuff. They have those same widgets, but they're for your terminal, right? Basically, what you do is you say, I want to take over the terminal, and I want to like render this stuff on the terminal. So each of these are like this is a block up here, and this is like a tabs widget, and then this is a tables widget, and I created like a little scroll widget, so some of these programs are really large. Then here's a widget that tracks the state of each process, and here are all the channels that are communicating with each other, and then here's my little box for my head. Like I said, this is why this is there. But anyway, I think it's really cool. I'll show you like kind of like a high level how it works. Obviously, because if you're looking at the if you're looking at the program, we need to know a lot about each of the processes, right? So like as I'm stepping through the processes up here, I need to know a lot about where they are and what they're doing. So you need to be able to track that state. And so obviously I need to know about each of the amplifiers, and I need to know about each of the channels. And but otherwise I can set it up, this code for, I'm just doing one permutation, but you can see like I've kind of set up the code to just process a single permutation, and the code doesn't look much different other than we have this little notifier for debugging, right? We want to debug it, so we want to kind of like step through it. So we use this notifier to tell each of the threads when you should like take the next step, right? And again, I didn't have enough time. I wanted to do like, and maybe as I have time, as we're working on more of these days of the intcode computer, we can have some fun with this and see how far we can go. If you want to keep working on it, or maybe you have some better ways of doing this, I'd love to see that as well. But the idea kind of being is like, ooh, could you use the debugger to do stuff like, after you've done a process, could you like change a value in memory? Or could you, in some debuggers, you can kind of like revert your last thing, or maybe as things get more complex, like maybe you're going up or down the stack, right? For now, we were just kind of going forward in time. So I need this notifier where it says, and again, I'm using a channel, but the notifier is saying, hey, wait until I tell you to process the next instruction, and then actually do that single instruction, and then stop there, right? But otherwise, then you just, here's all the TUI stuff is in this app. You create a new TUI that has access to all the amplifiers, channels, and notifiers, and then you just tell it to run, and it does all that stuff, right? So if I go here into my TUI code, you can see like this all came from using the Ratatui documentation, which I thought was really good. But basically, like, here's some setup code you have to do, here's some cleanup code you have to do, and then here's your like main loop if you've ever done like game programming or I don't know, any type of like UI programming. This is usually how it is like you do some setup, you do some cleanup, and then you have like a main loop where you like draw and pull for input and handle that input, right? Is like what you're doing all over the place. And that's all the run is. So all you have to figure out is, how do I handle events and how do I draw, right? And I'll just show you an example of like one of the draws. So if I want to draw the channels, which is like this purple section over here, I create a block, which will be this outline around it. And then, you give it some colors that you want to do, that you style it how you want to style it. And then I just enumerate over the channels and create like create a span for each of the channel values. So that's this chunk right here. And then I just style it based on whether it's the active one or the non-active one, right? So that's this part right here. And then I just tell it to, hey, render this widget in this chunk that I've given it. And the chunk that I've given it is this block right here. But then it allows me to step through the code, right? So if I go back to the initial process, you can see down here, I can have the step and the quit function. So I can hit Q to quit. And then if I want to step through, I can see, oh, I'm currently here, which is a 3, which happens to be input, and it's going to input at 8, which is pointing to this. So the red are the parameters, and then the blue are any positional parameters that they're pointing to, right? And so I can just hit step and it will process. And you can see here's the next instruction, which is adding these 2 values and putting them back there. So I do that and it processes. And you can just kind of keep stepping through, right? And eventually you get to a 4.9, which is an output. So if you watch over here, when I run this, it does its processing and sends its output over to this channel. So now I can move over to this process and do the same thing, and it will spit out to this channel. And we can just kind of do that. Anyway, I thought this was a kind of a fun way to visualize. If you're trying to understand how this works, again, this is how I kind of saw what was going on in part 2 when I was running this and visualizing it. As you can see, there's some of these processes do multiplies, and some of them do like low multiplies, and some of them do high multiplies. And so you might actually be able to infer by going through. You can think of this as like you're like reading the assembly of your program or whatever. Like as you're looking through it, you can say like, oh, clearly this one's multiplying by a high value, so I want to give the largest initial phase setting to this one, right? And that would give you the largest answer. But anyway, again, you can see how I can step through this and kind of do the processing until they're all done. And you can see here once they've all halted. So for this phase setting that I set up, I think it was what was it? 0, 1, 2, 3, 4. So there's the initial one. The final output of it is 10,028. Anyway, so that was it. I won't go over this too much, but as you see, I will probably keep trying to use this so we can kind of visualize things, especially if the computer changes or how things are going. I thought this was kind of a fun way to just kind of show it. And I'd be interested in what ways you do it, right? Maybe you're not solving it in Rust, but maybe you're doing like JavaScript or something like that. You could potentially do this inside a web browser as well. Obviously, there's other frameworks, right? I used a TUI, so I used Ratatui because I spend a lot of time in the terminal. I kind of, that's where my home is, even though I realize a lot of people have moved on from that. But so that's how I wanted to do it. But there's other ways to do it, right? Is like, Discord. The name went out of my head. Discord and that stuff. It uses like Electron, I think is what it's called. And there's a Rust version of that. I think it's called Tauri. I'm almost positively saying that name wrong. You've heard me call it VecDQ, right? So anyway, I'm almost certainly saying Tauri wrong. But there's things like that for Rust as well. So besides just creating a terminal interface, you could create something cool, right? And if you do, I'd love to see it. Show me what you got, and I'll happily try it out and run it. But okay, so given that we've done a lot of talking, again, I hope what you've gotten out of this is, first of all, AOC Advent of Code is a great way to learn to program, right? And to learn your language. You could do this with a list, and it's perfectly fine. But I wanted to stretch myself and make sure I really understood how threads and channels worked in Rust, because I honestly haven't done a lot of work with threads and channels in Rust, and so this was a great way to do it. And besides that, I hope that you've gotten an inkling for how powerful threads can be and how powerful channels can be, right? And again, what I mean by powerful is the simplicity of them that allows you to reason about your code, right? I didn't have to change anything about my amplifiers besides saying, okay, instead of using a list, I'm now going to use these channels for input and output. And then it just kind of magically worked. And that's what I think is so cool about these things is once you've got them in your toolkit of, problem solving tools, the magic that they can perform is amazing. And it's one of the reasons why I like Go, and I still use Go daily in my work. Is a lot of the work I do is this style of like inter-process communication, right? I've got lots of Go routines doing their own stuff. And when you were doing that in C using mutexes and I can't even remember the name, semaphores, it came to me. That was a long time ago. Using those type of things, it was really easy to like mess up and dork things up. But using these channels are very easy to reason about, and especially when you're in Rust, Rust won't let you make a mistake, right? Like if you tried to clone the receiver, it's just not going to work. If you tried to use that receiver in multiple threads, it's just not going to work. And so once it compiles, it's very likely that you've rigged this up correctly and it's just going to work. And that's what happened for me when I was solving the problem, right? I knew that I needed to do this stuff, and so I created the for loop and started creating the channels. And it just worked. It just solved the thing. And again, I was able to basically use the same stuff that I'd used from the previous day to solve the problem. I just used these channels. So, there you go. That's it. I hope, how many times do I say that in the video, by the way? Anyway, what I'll just end with is, I think what I'm going to do is, instead of moving on to the next day, I'm going to try and implement this in using async and await, which if you've used like JavaScript, for example, especially on the front end side, no, I said that wrong, especially on the back end side, most of like Node.js stuff is async await style. But they also do it in the front end too, like for web requests and promises and stuff like that. In Rust, they're called futures, but a lot of it is the same. The idea is asynchronous programming is the cool new thing. And using something like Tokio, which I'll give you a link to, is a great way to like get into that. And so I think for my next video, I'll switch this all over to Tokio. I think you'll be surprised at how little the code changes, I hope, because Tokio still has things like channels, for example. So we'll still be using channels, and you still need to spawn tasks, I think is what they're called. But instead of it being a thread, you can think about it as like a task that Tokio is supposed to process. And then the cool thing about it is Tokio will do the work of how much of this can I do concurrently, how much of it can I do in like parallel, with the differences between concurrency and parallel, actually being kind of interesting here. I actually don't know if it does it over multiple. Does it do it over threads? Yes, it is. Yeah. Okay, there you go. It creates as many threads as there are cores, but then you have multiple tasks, right? Go does this as well with its Go routines. You can think about Tokio and asynchronous programming, very similar to how Go does its threads and channels and stuff like that. So anyway, I think this will be a cool video where we can actually see how it works there. And then we'll move on to further days where we'll probably stick to asynchronous as necessary. just because it's the new cool thing. And especially in this case, we'll talk about the pros and cons, but threads are relatively heavyweight. Notice it says here that when you spawn a thread, you're spawning a native OS thread. So the underlying mechanism is, if you're familiar with C, you're literally doing like a P thread create, which is, again, not terrible, but it is a lot of work if you're not doing much with it, right? And I don't think I even showed this, but for the channel communication, because I wanted to show like what's on the queue, I actually had to create like this, my own little, I call it a channel as well, but basically I hook up two channels to each other to allow, and like the input channel puts stuff on a queue and the output channel takes stuff off the queue. But I do this in such a way that that's complaining about something right here. I can fix really quick. Sorry. Do you ever lose your train of thought like this when you're doing work and then the compile or like Clippy or whatever says, hey, you could do this a better way? Okay, so this way, do I have it in my thing? I can actually show you what it does really quick. Do you remember when I was wrapping this up a few minutes ago? Basically, I wanted to see what the data was in here. So I actually needed to have a receiver and a sender. And I actually used 3 channels to do that work. And the receiver is putting stuff off the queue and the sender is taking stuff off the queue. Did I say that right? Receiver's putting stuff on, the sender is taking stuff off. But I want to do it in like a synchronous fashion where I only do like, this can put as many things as it wants on the queue, but this one should only take one off one at a time as the output comes. And that's, so we use a sync channel here. Anyway, I have to create 2 threads, one for this one and one for that one. And they're not really doing any work besides just taking stuff off and putting it on the queue. All of this is to say, the cool thing about asynchronous is, if there is, because they're a task and not like a dedicated thread, Tokyo can do a really good job of saying like, oh, this thing only does a little bit. I don't need to, I'll allocate some time for it to do its work and then move on. And, some of the heavier processing things can be done in their own stuff. So that's the point of what I was trying to make here. Is there's some cool things you can do with asynchronous. And with that, I will say my final, that's it. I hope you enjoyed doing day 7. I had a lot of fun. I learned a lot about it. And we're going to keep doing this. We'll do the async await, and then we'll keep building out our intcode computer because I'm having a blast doing it, and I hope you're having a blast doing it. It's really fun to learn how to do this stuff. Whatever language you're doing it, if you're doing it in Python, there's still these type of things that you can do in Python, right, to do that communication. You can still do really fun stuff, and I'd love to see your solutions. I'll do code reviews. I promise I'm a positive code reviewer. I'm not going to bash all your terrible code because, quite frankly, my code is never up to snuff, right? I would never give my code an A. I always feel like I need to refine. So I'd love to see what you're doing. And I haven't looked at the day 7 solutions that you've already posted, but I promise I'll do that, and we'll talk about that talk about that next time, or we'll just I try and comment too, so I'll comment on your thing to see what it's like. And like I said, part of that was what led me to do the debugger stuff. So anyway, great work everyone, and we'll talk to you next time.